So thank you very much. It's really a pleasure for me to give this talk, even in this condition. I'm not in Vienna. I'm very happy to do it. So I will speak about some recent work with Ilaria Fragala from Polytechnic from Milano on rigidity for measurable sets, or alternatively, I could have named this talk sets with constant approximate mean curvature, or if you want, a sort of weak form of Alexandrov theorem. So let's see what it is about. So most of the talk, I will just describe the problem and some historical feature, and probably I will not really be able to enter into any technical details of the proof. So feel free to ask me after the talk information about that. So let me state the problem. So we consider a set. A priori, the set will be measurable with finite measure in Rn or Rd, and we fix a fixed radius, a positive radius small r, and we consider balls of radius r, so the radius is fixed, which are centered onto the boundary of the set. If it's a measurable set, we will center the ball on the essential boundary. If it's an open set, we center the ball on the topological boundary. So here you have such a ball. The radius here is r, so all the balls have the same fixed radius r. We center them onto the boundary, and we look to the measure of omega intersecting with the ball. And we assume that for all centers on the boundary, so when we roll the balls along the boundary centered here, the volume is always the same and equals some constancy, which is strictly positive. And the question is natural. Is it true that such a set should be a ball? So the set is measurable or open if you want, but not necessarily smooth. And it's definitely of finite measure. It's a very important information. So clearly, if you have a ball and you do this procedure with a fixed size for the radius r, all the time you'll get the same volume for the intersection. But now the question is this rigidity point here, and to understand whether or not we find the ball. So here it's a simple draw. But in fact, it is not absolutely clear. Then when you take even in 2 dimensions, such a rolling ball on the boundary with center at the boundary, the intersection with omega is so nice. So here I have a different example. So of course, depending on the geometry of omega, the intersection of the ball, the radius is fixed, may be very strange, as you see here in this example. So in this talk, I will discuss this question, and then I will give you some results that we have obtained with Ilaria Fragala. And more or less, it goes into the sense of the theorem of Alexandrov somehow. And so instead going directly to the proof, I will rather discuss some historical facets of this question. And I underline here 3 historical facets of the problem. So this makes reference to the so-called Bernstein problem, which was solved definitely in 1969, and it was set in 1915, on the Alexandrov theorem by Alexandrov in 1958, and some extension recently by Delgadino and Maggi, and on some recent works on the fractional perimeter. And somehow what I'm talking about, the previous problem, is related to all of the 3 here. So let me go ahead and recall you what is the Bernstein problem. So Bernstein in 1915 solved the following question. He considered function defined in R2 with values in R, so which produced surfaces in R3. So the graphs of such functions are surfaces in R3. And the question is, if you have such a graph, which is corresponding to a C2 function, and which has 0 mean curvature, then necessarily the graph of the function, it's a plane. So the function is affine. So this was the Bernstein problem. He solved the problem. So here is the equation. See? So it's a mean curvature equation. And he solved the problem in 3 dimensions. But one has to wait many years up to a full answer to this question. And in the 60s, the problem was completely solved in a sequence of series of results by Fleming in 62, who gave a new proof in 3 dimensions by a monotonicity formula for minimal surfaces. De Giorgi in dimension 4 in 63, Almgren in dimension 5 in 66, Simons in dimension 6, 7, and 8 in 68. And this problem was completely solved in 69 by Bombieri, the Georgian Giusti, proving that this is false in dimension greater than or equal to 9. And well, this is maybe the first problem to which I want to make reference, because in fact, the question to which we arrived on was related to Cimino. Cimino was an Italian mathematician, was professor in Bologna, but when he was young, in 1932, he was a student of Piccone in Napoli, I think, and he conjectured the following, or raised the following question. So imagine that you have a surface gamma in R3, which is smooth, but smooth, not so smooth that you can speak about mean curvature, but smooth enough to give sense to the surface. So let's say C0 surface. And he wanted to characterize all such C0 surfaces. So let me make a draw. So imagine that you have a surface here, such that he said, every time that you take a point on the surface and you take a ball of some small radius, so here you have the ball with small radius, so that the surface splits the ball into nice pieces that you can call the upper part and the lower part. And he wanted to characterize all such surfaces such that the area of the sphere above the surface is equal to the area of the sphere below the surface. And he said for every point on the surface, every center of the ball X, and every small radius, he said. So half of the area is 2p r square in 3 dimensions. And in fact, this problem is somehow related to the Alexandrov problem in some sense, because if the surface was smooth, then of course, if you have this information for every small radius r, using asymptotic formula for either for the volume or for the surface of the sphere, which has fixed first term, 0 order terms, and at the first order, you have the mean curvature popping up. So if you have the information required by Cimino on the surface, which splits the ball into equal area pieces, then you, if the surface was smooth, then immediately you get information on the equality of mean curvature, which has to be 0 in every point. But he said he wanted to study this kind of question because a C0 surface may not have curvature in the classical sense. So he said, in this way, if there is some limit for the half of the areas of area above, area below, then he said one could give some generalized sense to the curvature on such a non-smooth surface. So this was the question by Cimino in 32. So he raised this question in terms of areas above and areas below for any small radius, but by integration, immediately you observe that if you have this information for areas, you will get similar information for the volumes, so equality for the volumes above and below the surface. So he didn't give the answer, and he wrote the last paper in 88. He passed away in 89, and the problem was still unsolved at that time, and he just brought some new insights on the question. And in fact, some solution of the problem was given by Nietzsche in 95 to this. And in fact, he asked the surface to be C infinity. C infinity embedded in R3. And he proved that only C infinity such surfaces, which in particular have 0 mean curvature, so our minimal surface in R3, are the plane and the helicoid. And somehow, so this result, so you notice here the hypothesis, which is much stronger than the original one of Cimino. But later on, it was proved by Max and Rosenberg that the plane and helicoid are the only simply connected minimal surfaces embedded in R3. So this is kind of historical ground of the question. And it turns out that in a series of papers by Magnanini and Sakaguchi, they noticed this kind of questions when they analyzed the so-called Mazoch-Ball soup problem, which is kind of overdetermined problem for the heat equation. So this is related to the Bernstein problem. But now there is a second connection with the Alexandrov theorem, because you see what we have here in the asymptotic. So we have information on the volume intersected with the ball, this first term being always the same. So this is sort of approximation of the mean curvature. Okay, so Alexandrov in 58 proved that the balls are the unique bounded connected C2 sets, so which have a constant mean curvature. And the proof of Alexandrov was done by a method that he invented. It's called the reflection method, or in the community of the PD people, more known as moving planes method. I will, if I have time, I will discuss a little bit this proof. And this result was nicely extended by Delgadino and Maggi a few years ago, where they proved that they somehow removed the C2 regularity result a priori and the connectedness, and they proved that finite union of balls are uniquely the sets of finite Lebesgue measure and finite perimeter, which are critical for the perimeter function. Because constant mean curvature, which is a constant which is not zero, so in the case of the Alexandrov theorem, corresponds to sets which are critical for the perimeter when, let's say, locally you minimize perimeter at the volume constraint. And the proof of Delgadino and Maggi was not following the reflection method or the original reflection method of Alexandrov, was rather based on the Heinz-Karcher inequality for the curvature, mean curvature. And there is a third facet of this problem, is the so-called non-local fractional perimeter. So the fractional perimeter was introduced at the beginning of the 2000s and studied in a series of papers by Caffarelli, Souganidis, Caffarelli, Roquejoffre, Savin. And here you have the formula for the fractional perimeter, depending on some parameter here S is between 0 and 1/2. So you have a sort of kernel function. So it's 1 over x to power, let's say, x to power d plus 2s, which has this kind of graph. Here is the singularity. And one defines this notion of fractional perimeter, which is related somehow to the fractional Laplacian. And soon after this introduction and study, there was a result by Frank and Seringer proving an isoperimetric inequality for the fractional Laplacian, for the fractional perimeter, essentially stating that the ball at fixed volume has a minimal fractional perimeter. And naturally, this came to the study of the so-called sets with constant fractional mean curvature. And the fractional mean curvature here is defined here with this integral in principal value. So now there was simultaneously, there were two results by Ciraolo, Figali, Maggi, Novaga, and by Cabré, Fall, Sola Morales, and Veth in 2018, proving a sort of Alexandrov rigidity result for the fractional perimeter. Namely, if you have a set omega, which is bounded open and of class C1 to S, so quite smooth, with constant fractional mean curvature, then omega is necessarily a ball. So now our problem somehow goes in this direction. So it takes a little bit from Bernstein, Alexandrov, and the fractional perimeter. Because in fact, the quantity at which we look, which is the volume intersected with a ball, can be associated to a so-called generalized perimeter, recently studied by Chambol, Morini, Ponsiglione, or Mazon, Rossi, and Toledo, which is associated to some kernel function. So given a function h, which is decreasing radial, for instance, locally integrable, non-negative, and so on, one can define a generalized perimeter, P, let's call it P depending on h, in this way, which is somehow similar to the fractional perimeter, with a difference that the kernel here, it's this function h. And associated to this, one can associate a sort of curvature, mean curvature, defined in this way. So in this context, what we asked for the constant omega intersection, the volume of omega intersection with the ball, corresponds precisely to taking the kernel, the characteristic function of the ball. So instead of considering the kernel, which was 1 over x to power d plus 2s, which has a graph something like that, our kernel has a graph which is something like that. So, and the associated, let's say, mean curvature associated with this kind of kernel function, which is the characteristic function, would be equal exactly to the difference between the volume of omega intersected with a ball and the complement of omega intersected with the ball, which is 2 times our constant minus the volume of the ball of radius r. So these are the sets that we want to study finally. So going back and putting this into the context, we want to study sets which have constant mean curvature associated to the kernel, which is the characteristic function. So this is the way in which we define our critical sets. So these are sets satisfying for every point on the essential boundary of these measurable sets that the volume of omega intersected with a ball is constant. And just let me tell you one word that, in fact, these kind of problems appear, this is the way in which we arrived to this question, in the context of the analysis of critical sets for the Riesz inequality. But there is a second application that we found later in the geometry processing or in discrete geometry. So in discrete geometry, people work with sets which are essentially pixelized. So they are a union of points. And they want to find some features of those sets, in particular, a sort of weak notion of curvature, of mean curvature at the boundary. And one way to do this, so is to take a boundary point. So let's, in my case, this would be the boundary point. And then what they do, they take this point, they center balls with some radius, and they compute the volume of the set intersected with the ball. Here, the volume means the number of pixels from the regular grid inside the set. And they do this at different scales, and they want to find some kind of, to extract some kind of behavior and to say that, to give some information in terms of some kind of weak curvature. So now coming back to our problem. So I said, in fact, so as comparison, this would be the graph of the kernel, 1 over x to power d plus 2s, and this is the graph of our kernel. And in fact, even though both problems somehow can be put into the same kind of framework, so the kernel, which is the characteristic function, is really very different and behaves totally different from the fractional perimeter. So the first fact is that our kernel, which is the characteristic function of the ball, is bounded. And the fact that it is bounded, it's bounded by 1, of course, allows us to integrate it locally, to integrate it against any measurable set. So we can deal with measurable sets. On the contrary, if you look to this kernel, because of the singularity at the origin, you can associate this kind of fractional perimeter to sets which enjoy, and particularly curvature associated with fractional perimeter, which do enjoy some smoothness. So this is the first fact. The second fact, which is typical for this kernel, it's the flatness of the level set. So we have, in fact, only 2 level sets here with strictly positive measure. And this makes that somehow, this makes the problem more complicated, because if we have a point here where the kernel function takes the value 1, we don't know where exactly it is inside the ball. We know just it is inside the ball because the kernel function is valued 1 at the kernel. If you take for this kernel here, for the fractional perimeter, a point, and you know the value of the kernel, you know precisely at what distance you are from the singularity. So this is a kind of bad behavior of this characteristic function of kernel. Also, a new point is that our kernel is with compact support. In other words, we don't really know what happens starting from some distance far away from the set omega. So it's a sort of short range non-local. It's non-local, but short range, because at some distance, its effect is blocked. It's blocked precisely because the support is bounded. The support is bounded. And there is another important difference, is the fact that our kernel is discontinuous. Oops. Oh. I'm locked. So it seems that my tablet stops to work for some reason. So then what I do, I switch on the, okay. Okay, so let's see if it works. Okay, let's try. Okay, it's good now.
Yeah, looks good.
Oh, so it's so I was exactly here saying that this kernel is discontinuous, and this produces kind of strange effect. And because of the discontinuity, in fact, we need some kind of non-degeneracy condition in order to get rigidity. So let me explain. So first of all, what is our non-degeneracy condition? Very shortly is the following. So somehow we can say things about sets which do satisfy the following property. We take points on the boundary, 2 points, x1, x2. We center balls of the good radius on the boundary, and we look to the symmetric difference of their measure inside omega. And if this symmetric, the measure of the symmetric difference inside omega divided by the distance between the 2 points is somehow minorated over the boundary, then we said that our set is non-degenerate. Roughly speaking, a sufficient condition to do this is to satisfy the following property here. We take balls of radius r, we center them onto the boundary, and we want that, let's say, the surface, the Hausdorff measure of the sphere inside the domain, it's minorated from below. Okay, but for instance, this non-degeneracy condition is satisfied for any open connected set, provided that the radius of the ball is strictly smaller than the diameter. So it's a quite transparent condition. And here is our result with Ilaria Fragala. So we consider a measurable set with finite Lebesgue measure and a fixed positive radius r. Assuming that omega is critical. Critical means that every time we center balls onto the essential boundary, the volume of the intersection is the same, is equal to positive number c. And assume that the set is non-degenerate, satisfying this condition, then we obtain the rigidity result saying that omega is equivalent to a finite union of equal balls of radius r greater than the distance small r divided by 2. So we not only obtain information on the geometry of the ball of the set, which is a union of balls, but the balls have to be a little somehow far away at some distance depending on r. So now this non-degeneracy condition, I will give some examples showing how it is important somehow, but in fact it's transparent in the sense that as soon as a set is open and connected, then the non-degeneracy condition is automatically satisfied. By the way, if omega is measurable with finite perimeter and is decomposable with a radius r, which is again strictly smaller than the diameter, the non-degeneracy condition is satisfied for free. So in other words, we don't really need it. But in order to give some kind of general result, we put this technical hypothesis here. But in the common situation is not such. So now let me give you some examples. So what are the sets for which are not rigid in view of our results? So first of all, there are sets which are not rigid, are not balls, union of balls, if they have infinite measure. So typical case, if you have here half space, like this, or if you have here an infinite strip, you put balls, definitely you get the same volume for the intersection, but they are not, they do not apply, the theorem does not apply. And this is the case because omega, the set, has infinite measure. Now, here I will show you examples of sets which escape from degeneracy, or because of the degeneracy hypothesis. So typically, imagine that the radius is quite large. So this is the radius r here, So you have the ball of this radius r, and imagine that the set is small. Well, if the set is small in diameter, of course, as soon as you put a ball here of radius r, you will cover all the set. So you cannot distinguish anything. And this is a consequence of the flatness of the kernel. Or we can imagine sets of large diameter. These are unions of small sets, and again, this kind of property occurs. Or even somehow worse, we can imagine this kind of situation here in which the ball somehow goes between the small sets. So every time we center a ball, this will somehow avoid the sets. We can build such sets. So, and this is precisely related to the non-degeneracy hypothesis. But as I say, as soon as omega is connected, so non-degeneracy is not relevant. Now, in the very 2 minutes that remain to me to discuss this, so let me try to speak some words about the proof. So the proof somehow follows the Alexandrov idea of reflection method, which was very much used in the study of order-determined problem, which roughly speaking is something like that, to be very, very quick. I'm sure that most of you know that. So we want to prove that the set satisfying, here is the example of Alexandrov, constant mean curvature, smooth set with constant mean curvature. We want to prove it is symmetric with respect to any hyperplane. So we fix a hyperplane. Here is the vertical direction. We move it in a parallel way. And at some point we become tangent. And then as we move it, we reflect the sets inside. So here you have a situation of reflection inside. The set being smooth, you can start to do this movement. At some point, the movement will stop. And there are, roughly speaking, 2 ways in which the movement will stop. Either that the reflected set will touch the original set omega, that's omega, in some point like here. Or if you get some kind of orthogonality at the contact with a hyperplane, in which situation you don't know if you can continue the movement, because if you would continue in this way, somehow the reflected set will get out around the contact point. Now, Alexandrov, in both situations, proved that the reflected set has to coincide with the original set omega, studying the nonlinear PDE of the mean curvature equation. And by some kind of maximum principle applied here, or by Hopf principle applied there, he proved the coincidence of the sets. And this being done in every direction, then omega was a ball. So what is the situation in our case? So in our case, the situation is that we work with measurable sets. And as we work with measurable sets and we somehow want to follow the same idea, there is a fundamental difficulty even from the very beginning, because you see here, this, assuming this is omega, it's Lipschitz, it's not C2, it's just Lipschitz, and you want to produce the same kind of reasoning. So you come here and you want to reflect, but you see the reflected set, because it is not smooth, immediately goes out of the set. So you cannot even start the movement. And similar behaviors, very bad behaviors occur. I mean, maybe not this is the worst, but this notion of orthogonality does not have sense in the context of measurable sets. So in fact, all our work with Ilaria Fragala was somehow to rebuild the Alexandrov method in the context of measurable sets, and to prove that the movement can start, so the movement can start, and to understand why it stops here and there, and why, when it stops, this implies the equality, the coincidence between the reflected part and omega. So roughly speaking, these are the ideas. So I will not enter the details. I'm just going to my last but one slide. So now this leads to a natural question. What happens if we replace our flat kernel with another one? So here we have some result with Ilaria Fragala, which says that in general, the result is true, but depend very much on the structure of the function h. And then a very interesting question to which we couldn't answer is answer somehow the original question of Cimino, and to look to the areas of, so let's say this is omega, and not to look to the volume, but to rather look to this area of the sphere intersected with omega, but of course for a single radius r, not for all the radii, and to understand whether or not one can get some kind of rigidity result. And to finish, just to say that, in fact, we arrived to this problem by a completely different way, because we were interested to find some polygonal isoperimetric inequalities of Riesz type, in which situation we arrived by searching for criticality exactly to this kind of question. So thank you for your attention.
Thank you very much for your presentation. Are there any questions? Please. Yes, Gianpaolo?
Yes. So the question is about the case of infinite volume. So I didn't catch if you said that in that case you only can have, say, strips or slabs or half spaces.
We don't know. So no, these are just
okay.
examples. These are just examples showing that the result cannot hold, but we don't know if these are the only.
Okay.
I don't know. So that's a good question, but I don't really have a clue on how this could be done.
Thank you. Thank you very much.